Well, hello guys, here Mr. G with another question for the grade 12 related to rate of reaction mostly. This is going to be question 4 from still the test for rate of reaction, but this question is the question 4 for the challenge 1. Vehicle with engine that are broadly turned are a healthy risk. In such vehicles with limited supply of oxygen, octane burns in complete and formed carbon monoxide as shown below here. 4.1. If 500 grams of octane burned at SDP, calculate the volume of carbon monoxide that will be released into the atmosphere. Okay, so here we have the chemical reaction, and they are telling you that 500 grams of octane is burned. So the mass of octane that burned was 500 grams, and this one was at STP. It is important. It is very important to know that is at STP, standard temperature and pressure. Okay, now they say calculate the volume of carbon monoxide that will be released into the atmosphere. So you have to calculate the amount of carbon dioxide that was produced there. Okay, the first thing we're going to do is to calculate the number of mole of octane, guys. Number of mole is equal to mass divided by molar mass. Mass is 500 and the molar mass is 8 times 12 plus 18 times 1, which is the molar mass for hydrogen. Okay, so that one is, all these numbers are coming from the periodic table. So the number of mole for octane that was used or burned in this case was 4,39 mole. Now what are we going to do then? Always we're going to do the same steps. Now we're going to use the ratio. Now the ratio of octane, which is C8 H18 to carbon monoxide, because that is the question. Okay, so the ratio. Now the ratio, remember, are the numbers at the front, guys. These are the ratios there. So in other words, it's 2 for this one and 16 for carbon monoxide. So now it's coming the question. If you have 4,39 mole of this one, how much of this one you can get? And this one, guys, is cross product here. So you have to do cross product. Very simple calculation there. When you do the cross product, you get 2n is equal to 4,39 times 16. And this, at the end, you will get that n is equal to 35,12 mole. So to used up 4,39 mole of octane, it will produce 35,12 mole of carbon monoxide. And guys, now we have to calculate the amount there, the volume of the carbon monoxide. Now what formula we are going to use here? We are going to use the formula number of mole is equal to volume divided by molar volume. This formula, guys, let me show you. It is here. Here is the formula we are going to use. Now remember, this is for gases, that is at STP. If you have STP, it's not at STP, it's for gases, but the molar volume is here if it's at STP. Okay, so that is what we are going to be using right now. You're looking for volume. So volume from here, if you rearrange, I am going to rearrange even though I don't like it. I like to substitute first. So volume is equal to number of mole multiplied by the molar volume. And therefore this one is 35,12 multiplied by 22,4. So the volume is going to be 786,68 cubic decimeters. This is the volume of carbon monoxide produced or released when that amount of octane is burned. Okay, Now I want to point something out. This answer here may be a little bit different, guys, according to your rounding off. So remember, you have to round off in this question. If you do not round off, which is actually what's supposed to happen, then this answer may be slightly different there. Okay, so please know that one. I rounded off here and then I again rounded off somewhere there, but you please don't round off. If you don't round off, the answer would be 785.97. This is without rounding off. Okay, I round off all the answers and all the calculations before them. So we carry on, guys. Here we are. Now the next question says the Maxwell-Boltzmann distribution curve given below show the kinetic energy of the particles against number of particles when the catalyst is used. And there is the graph. EA represents the activation energy. Define the term activation energy. And guys, the definition of activation energy is the minimum energy required for a reaction to take place. Which one of A1 or A2 labeled in the above graph represent the activation energy when a catalyst is added? Okay guys, this one is here. The activation energy is this one. This one here will represent the activation energy, and this one will represent the activation energy with a catalyst. I'm going to write a C here for catalyst. Okay, that one is the one. EA1 represent the one with catalyst. Okay, that is EA1. That is the one with a catalyst because the activation energy became less. What effect does the catalyst have on the activation energy? It does lower the activation energy. It does lower the activation energy. Draw a sketch graph of potential energy against progress of reaction for an endothermic reaction and label the curve as A. Indicate the reactants, products, and activation energy on your graph. So here you have to draw a graph. We're going to do it on this case here. Okay, so here is the graph. This is the curve for an endothermic reaction. Remember, energy is being absorbed here. Okay, now they say for an endothermic reaction, now label A, this A indicate the reactants. Here is going to be the reactants. Indicate that the product is going to be here. The product, when we say reactants and product, is in actual fact the energy of the reactant and the energy of the product, and the activation energy of the graph. Now the activation energy is going to be the distance from here, from this point to the activated complex. This one here, guys, is the activation energy. I'm going to write EA. That one is activation energy. Okay, that's all they want. On the same side of axis, as question 4.5.1, draw a curve to show the effect when a catalyst is added and label B. So guys, it's very simple. The catalyst, all the catalyst is going to do is to lower the activation energy. So everything is the same. I'm gonna try to draw it there next to it with another color, but now here, instead of going so high, the activation energy is going to be less and it will be moving there. This graph is going to be now B. This one is B with the activation energy. After you add a catalyst, you can see that the catalyst, all it does is lower the activation energy. You see now it's less energy needed for the reaction to begin. Guys, this is the question. The question said level the curve B, and then is nothing else to add in there. So that is the question, guys. I hope you understand. This is question 4 from this other test related to the rate of reactions. I hope it helps. Subscribe for the channel. I'll see you next time. Mr. G here.